Hey everyone, this is the Introduction to Computing and Programming in Python, a multimedia approach, the fourth edition, chapter 5, Picture Techniques with Selection. So the learning goals for this chapter are to implement controlled color changes like red eye removal, sepia tones, and posterizing, to use background subtraction to separate foreground from background images and to understand when and how it would work. To use chroma key to separate foreground from background, or sorry, from background images. To draw lines and borders based on position. The computer science goals are to use conditionals to select certain pixels, to use if, else if, elif. So I want to make a change red function that will let me do the following. So we define a function called changeRed. It takes two parameters, picture and amount. There's a for loop that says for p and get pixels of the picture. So we're gonna iterate through every single pixel that's in that picture object, and the value equals. So we're gonna get the red value from the pixel, and then we're gonna set red, um, the pixel times what it was. We're gonna set the red pixel to the value of what it was times the amount. So if B is the Big Ben picture, which of the below did this? So we can see that it looks like the red was actually extracted. So it's not 1 because that's 1.5 times whatever the value was. It's definitely not 2 because that's 2 times what it was. It's either 0 or zero point 0.5. It looks like it was totally removed, so we can assume that it's probably 3 as the correct answer. So the distance between colors. Sometimes you need to, for example, when deciding if something is close enough match. How do we measure distance? Pretend it's the Cartesian coordinate system, the distance between 2 points. So we're all familiar with this. So we can see the distance between two colors is red 1 minus red 2 squared plus green 1 minus green 2 squared plus blue 1 minus blue 2 squared, and then the square root of all of that. So we can trying the distance function. We can see that the distance between white and black, distance between white and pink, distance between black and pink, and so on and so forth. So introducing if. So if, and then we have a test, and then we have a colon, and then we have the pound sign or the hashtag. It says these Python statements will execute. If true, print this is true, and then print this will print either way. So computers make choices. They can perform tests, and then they can execute different statements depending on the result of the test. So tuning our color replacement. If you want to get more of Barb's hair, as one of the examples we did previously, just increasing the threshold doesn't work. Wood behind becomes within the threshold value. So how could we do it better? We could lower our threshold but then miss on some of the hair, or we only work within a range. So computing a distance between two colors. What does it mean for a color to be close to another color? We will compute a color distance based on the formula for the distance between 2 points, which we showed previously. So replacing colors using if. We don't have to do one-to-one changes or replacements of color. We can use if to decide if we want to make a change. We could look for a range of colors or one specific color. We can use an operation, like multiplication, to set the new color, or we can set it to a specific value. It all depends on the effect that we want. So removing red eye, for example. When the flash of the camera catches the eye just right, especially when light-colored eyes, we get bounce back from the back of the retina. This results in red eye. We can replace the red with a color of our choosing. First, we figure out where the eyes are, x, y, using media tools. Then we can write a function called removing red eye. So the function is defined called remove red eye. It passes 1, 2, 3, 4, 5, 6 different parameters. We have picture, the start x, start y, end x, end y, and then the end color itself. So we go through all the pixels we look at in this line. We're looking at the distance. We're looking at a certain area. So x is between these start and end x. Y is between start y and end y. And then if the distance of between red and the color is less than 165, then we're going to set the color to whatever color we want it to be. So what we're doing here, within the rectangle of pixels, start X, start Y, end X, end Y, we're going to find pixels close to red, then replace them with a new color. So fixing it, changing red to black. So we can see that we pass in the variable Jenny, which we can assume is the picture object. We give it the coordinates of our rectangle over the eyes, and then we actually say make color 000, which we know is black. So Jenny's eyes are actually not black. Could fix that. But eyes are also not monocolor. A better function would handle gradients of red to replace gradients of the right eye color. So consider this program. Which picture below did this generate? So there's a function called fixFlowers1 that passes in something called arch, which we can assume is just a variable name based on the picture. Um, Not the best variable name unless there's multiple pictures, but arch doesn't really make too much sense when the function is more generic. But beside the point, we'll assume that the arch variable is named after the picture. So it says for p in get pixels of arch. So go for every pixel in the arch picture object. And it says if get red is greater than get blue plus get green. So if get red is greater than get blue or green, then we're going to set the color of whatever that all the red to yellow. Um, so we know it's not going to be which picture did this generate? So we know for sure all the red is going to be removed, so it shouldn't be too much. But this is only if the red is higher than the green and the blue combined. So we could probably assume that it's either 1 or 2. It's most likely not 3. Um, so because there's a lot of red here still, and there's not a lot of red here, as in this big blob here, we can assume that it's probably number 2 that was the actual answer. Here we have a different if get red is greater than 50 and get blue and get green is less than 200. That's going to be a more dramatic effect, I would assume. Um, so we could probably assume that it's probably more like number 3. And then we have another example as well. So this is saying if this is the distance between the colors. You can take an example like this that's similar and try. You can find a similar arch and try something similar with this as well. This is saying if the distance between whatever the color is in green is less than 200, set it to yellow. So it's looking for things that are pretty close to the color green. So based on that, we can assume that it's most likely um, probably number 1 or number 2. So posterizing is reducing the range of colors. See, we can see in the left picture, this person has quite a few different shades and different colors, and on the right we can see that those numbers of colors are reduced to be more simple, more like a cartoon drawing. So how we do it? We look for a range of colors, then map them to a single color. If red is between 63 and 128, set it to 95. If green is less than 64, set it to 31, etc., etc. It requires a lot of if statements, but it's really pretty simple. The end result is that a bunch of different colors get set to a few colors. So as you can see here, there's a ton of ifs. If red is less than 64, if it's greater than 63 and less than 128, yada, yada, yada. And that's how we do a posterization. So what's with the hashtag stuff? Like we said before, you can see quite a few hashtag or pound signs, whatever you want to call them, number signs. 1, 2, 3. This one just says loop through the pixels. I think we already covered this, but any line that starts with a hashtag or pound sign is ignored by Python. This allows you to insert comments, notes to yourself or another program that explains what's going on. When programs get longer, there are lots of pieces to them, and it's hard to figure out what each piece really does. So comments can definitely help with that to remind yourself or others who maybe are working with you about what you're actually trying to accomplish with these different methods that you might be using and so on and so forth. So posterizing to black and white levels. We can check the luminance on each pixel. Sorry about that for that word. If it's low enough, it's black, and otherwise it's white. So we can add the red, green, and blue together, get the average of that. If it's less than 64, it's black. If it's greater than 64, it's white. Another way to do it, we don't have to do both tests. We can just say else, right? So uh, this is saying if it's less than 64. Well, if it's not less than 64, we know that it's greater than 64, right? So we don't have to say if this or if this. We can say if it's less than 64, do this. Otherwise, or else, do this. It's easier to write and it's definitely more efficient, but it can be harder to read, especially for new programmers. So generating sepia toned prints. Pictures that are sepia toned have a yellowish tint to them that we associate with older pictures. It's not directly a matter of simply increasing the yellow in the picture because it's not a one-to-one correspondence. Instead, colors in different ranges get mapped to other colors. We can create a mapping using if statements. So we can see here's an example of a sepia toned print. We can see that it's not just an increase of yellow like we said. It's making the picture look like it was created a long time ago. So here's how we actually do it. We loop through the picture to tint the pixels. So we tint the shadows. If the red is less than 63, we multiply the red by a certain amount, tint the midtones, we tint the highlights, and then we set the new color values. So what's going on here? First, we're calling grayscale new. Um, this one with weights. It's perfectly okay to have one function calling another. We then manipulate the red and the blue channels to bring out more yellows and oranges. Why are we doing the comparison on the red? Why not? After grayscale conversion, all channels are the same. Why these values? Trial and error. Twiddling the values until it looks the way you want it. So edge detection. Blurring is averaging across pixels. Edge detection is looking for differences between pixels. We can draw lines that our eyes see where the luminance changes. If the pixel changes left to right, up and down, we make our pixel black, otherwise we make it white. Background subtraction. Let's say you have a picture of someone and a picture of the someplace, some or same background without the someone there. Could you subtract out the background and leave the person there? Maybe even change the background? Let's take that as our problem. So here's a person named Katie, and here's our background. Let's put Katie on the moon, as we can see on the bottom. So where do we start? What we most need to do is figure out whether the pixel in the person shot is the same as in the background shot. Will they be exactly the same color? Probably not. So we need some way of figuring out if the two colors are close. So remember this function that we did before? We're not going to go through this, but if the distance between the color and the brown is less than 50, we increase the red. So we can say that in the picture we increase the red value. So using distance, we know that we want to ask if the distance between the person color and the background color is greater than some value. And what do we do then? We grab the color from another background and new background at the same point. So do we have any examples of doing that? So where are we so far? We're saying if the distance between the person color and the background color is greater than some value, the background color equals a new background x and y, and we set the color to the background color. So what else do we need? We need to get all these variables set up. We need to input a person picture, a background picture without a person, and a new background. We need a loop where x and y are the right values. We have to figure out person color and background color. So we'll swap a background using background subtraction. I have a function called swap background, goes through all the pixels in a picture, and it gets the pixel from the background at x and y. It gets the color from the pixel, and then if the distance between the pixel and the background color is less than 15, we get a new color, and we set the color. So that is called a threshold, and we can see that that works. So there's our picture of Katie on a different background. But why isn't it a lot better? We've got pixels where we got pixels swapped that we didn't want to swap. See Katie's shirt and stripes. You can see that there's some background showing through. We've got places where we didn't want the pixels swapped, but that we didn't get them swapped. See Katie made a shadow. How can we make it better? What could we change in the program? We could change the threshold some value. If we increase it, we get fewer pixels matching. That won't help with the shadow. But if we decrease it, we get more pixels matching. That won't help with the stripe. What we could change in the picture: take them in better lighting, less shadow. Make sure that the person isn't wearing clothes near the background color. So here's an example, and we want to know what calls this function like this. Um, how do we see the result? Okay, so we say kid equals make picture. We get a picture of a kid, we get a picture of a wall, and we get a picture of a jungle. Kid, wall. We pass in three: kid, wall, and jungle. So how do we see uh, the result? So what we're actually doing, right, is we're modifying the new background with how it with the kid right from the wall. So we should explore the jungle picture, option 3, and we'll see our modified picture at the end. So playing with this program, you generate the above image. What did you predict changes? Did you make the threshold value too high and so too many pixels are matching both foreground and background? You made the threshold value too low, so too few are matching. You changed the if that you inverted the swap, or the jungle color is too close to the wall color and the moon would have worked better. So we can see that it kind of looks like Katie's cut out, but it's just Katie's silhouette. Um, so the swap does look like it actually is inverted. So 3, I believe, is the correct answer. So putting a dog on the moon, we can see a dog sitting in the chair left and a chair without the dog on the right. And we're able to actually remove the background using our swap background function, and then we can explore the dog picture, and we can see that the dog is placed on the moon. Another way we can do things is chroma key. You'll definitely use this chroma key as something in the future, so make sure you look in your book at some chroma key examples as well. But chroma key is having a background of a known color. Some color that won't be on the person that you want to mask out. Pure green or pure blue is the most often used. And this person, he used his son's blue bed sheet. So this is how the weather people seem to be in front of the map. They're actually using in front of a blue sheet. So here's a chroma key recipe. And it takes a source and a background, and it goes through. And if the red and the green are less than the blue, then we set the background color. Oops. So then there's the result. The blue sheet is totally gone, and it's replaced with both a moon or a jungle. So trying to make obvious thing for red. So here's another example of chroma key, 4 pixels, and then it compares them, and then it sets the color again. Couple less lines than it was before. But it doesn't always work as you expect, right? So you have to play with the threshold. But it's easy to do with this picture of Alice, right? Because the background's perfectly the same color. So we can see that Alice is easy to place in the jungle. So drawing on images. Let's skip that example for a second. Let's skip that. So lightening half the picture. Here's a function called right half bright, which takes in a picture. The halfway equals the get width of the picture divided by 2, right? That's the midpoint, or just the half of the picture. We go through all the pixels. If it's greater than the halfway point, we set a color, and we say make lighter the color. So we just lighten the color on half, and you can see that that worked for the right side of the picture. Here's a couple more programs. We'll skip these. Posterizing to 3 levels using elif and else. So we posterize. I don't think I said posterize before. Either way, I think it's fine. We do that with black, white, and red. So we get the red, green, and blue values. Check the luminance. If it's less than 64, we make it black. If it elif, which means else if, we're saying else if the value is greater than 120, we set it to white, and then otherwise else, right? Anything else is going to become red. And then we can see there's the output of the picture where this person is created in 3 different colors, and we used the if statement to accomplish that. So that's all that chapter 5 has that it entails. Quite a few different things. Be sure to look at chroma key because there is a homework that will be on that concept. So make sure you're familiar with that. If you have any questions about any of the examples, feel free to shoot me an email. Uh, Hopefully this makes sense. Take these examples, go through them. That's all. So if you have any questions, as always, feel free to email me. Thanks, guys.